Okay, so we are going to start the lecture today. As we were discussing, yesterday was quite a long lecture, and in particular, I didn't give you enough time to go over the neural network notebook, which I think is very important. It's something that you are certainly going to use if you keep doing machine learning. And to me, it's important that you have the time to actually explore what's going on in the notebook. For example, not only understanding the different things that are, or the syntax that comes with keras and the sequential building of a neural network, but also the different parameters that you can do, adding regularization and so on. I see in the Slack that some of you started improving on the issue of overfitting by adding some learning rates, some regularization to the problem. So that's great. So what I would like you to do is to continue exploring that kind of notebook. Now, I hadn't planned on this in the sense that the next step would have been unsupervised. So my plan for today is that you guys work on this notebook if you haven't done so, and keep working on it. But also for those of you who already went through it and won't take 3 hours, let's say, to continue exploring, I wanted to give you additional tasks, something where you can actually learn something new and additional to what I had planned for the course. And this is here. So you go to the Indico of the course. You see that as an additional exercise, I allow you to do a supersymmetry example from a paper. There are two reasons why I want to do this. One, because some of you will be working on particle physics and phenomenology of particle physics or experimental particle physics, and might be familiar with SUSY and searches or searches in general for new physics, and this might be useful. And the second reason is that in this paper, which is this high bias, low variance paper that I mentioned at the beginning of the lectures, they go over a data set of supersymmetric searches, and they do three things to it. They try to find new physics using a simple logistic regression analysis. So remember, yesterday we were talking about binary classification. We were talking about how when you want to decide between, let's say, new physics and standard model physics, you could use this cross entropy, this cost function, and run the usual, more traditional statistical learning analysis. This is precisely done in this notebook, again in Jupyter, so you can go over it. But also they go and use this example as a way to introduce decision trees, random forest, XBoost, and so on. And then they also use deep neural networks, in this case in PyTorch, in Keras, to do this kind of analysis. So for those of you, the people who are just trying to learn the notebook of yesterday and trying to get better at it, please keep doing that. The people who are a little bit more advanced, they can spend the morning precisely going over these things. Why, for those who are a bit more advanced, I like them to do this analysis. It's also because they talk about a technique I'm not going to discuss at length in this course, but it's also important. And those are decision trees, okay? So let me tell you what decision trees are and what is their use and so on. And then I will let you go and and do your work on the neural networks. Okay, so the idea of decision trees is again a classification problem. You start with the same building blocks if you want. You have data and you have labels. And what you would like to do is to build trees of a decision of the type of, for example, if some parameter xi is bigger than some number, then do one thing or then do another thing. And you would like to start building trees of decisions where essentially you start with the data, the xi, you start adding conditions to it, and then you move in one direction or another. And those decision trees can be very complex. Let me give you an example, otherwise it's all too, abstract. Imagine that we want to do the following. We would like to build a model that is a good predictor for, well, let's say, scores of your students in some subjects, let's say math scores or physics scores, right? So you would like to know, if you know the characteristics of your students, what would be a good predictor of what their scores will be. Those students, the characteristics could be stuff like what is their age, I don't know, the previous score in math or in language or English or whatever. You could also add as characteristics for the student things like how many hours they declare they study. You might also want to add other characteristics like the number of hobbies that they declare to be serious hobbies. Let's say they play guitar or they are in a band or whatever. Or, for example, you would like to add stuff like the level of studies completed by their parents, or what kind of environment for study they have. Let's say, for example, you could give a score as the fact that the students, when they go home and they study, or they go to the library and they study, it's a good environment for study. Okay, so when we say students, we mean a lot of possibilities, a lot of possible characteristics that may determine or influence their final math scores. Okay, so for example, you could start building possibilities for these decision trees. For example, you could start by saying, I'm going to build a tree that says that it will start with taking the previous score in the same subject in math. And if this score is bigger than some value, let's say bigger than B, you go in one direction. And if it's smaller than B, then you go in another direction. Then you might decide that your next level of importance, of feature importance, is going to be the hours of study, right? Hours of study. And then you may start branching. And here, for example, you might start also thinking or have more than one branch. It could be that you do 1, 2, 3 hours of study per day or whatever. And here you might start also wondering about the influence of the age, the number of hobbies they had, the level of studies their parents had, stuff like this. And you can build many of these decision trees, right? And changing the thresholds for each of these decision boundaries, changing the structure of the decision boundaries as well. And if you build many of those, you might end up finding a very good predictor in the sense that, given characteristics of a student, all these things over here, you pass them through this tree and you get a math score predicted that is very close to the real math score that the student will get. Okay? So you think on this, this is you are exploring many possibilities, many intercorrelations between the different features. You are also, in some way, when you build a tree, by placing, for example, this characteristic as the highest one, you are giving it some kind of more importance than the others because it's the one that is going to branch first. And maybe later on, the previous score appears again, and again you are doing branching, and that reintroduction of this feature might increase your performance. All these are indications that previous score might be a very important feature, whereas other softy things, like for example the number of hobbies, might be not that important because they just don't influence the final score that much, or even the environment of the study and so on. By building these trees and realizing what structure fits the data best, you might also understand what features are important. So decision trees are used to try to, well, of course, get better predictions, but also to understand feature importance. Okay? Sorry, my handwriting is terrible, but that's what it is. Okay? So all this kind of analysis is good when you actually want to understand what kind of a characteristic of your student influenced the final decision the most. Now, these decision trees are not computationally very efficient as compared with neural networks. They don't have the same level of expression. Okay, and also they tend to overfit. So typically, when you talk about decision trees, you immediately, and decision trees can be things like random forest and so on, they immediately need to be taken as a grain of salt and start doing some regularization because they tend to overfit. But despite all these negative aspects, so lack of efficiency in computational power, or the fact that it's not very expressive, or the fact that they overfit, we still like to use them because in this context, in the context of random forest or decision trees, sorry, you are going to have some understanding on what features are more important. So, for example, out of an analysis like this, where you try many possibilities of algorithms and you see which one predicts the best, you may end up having a kind of table that tells you that the feature importance of previous score is much bigger than, for example, the fact that you have a number of hours of study, or, for example, that the other features, let's say like the level of studies of their parents or the hobbies or whatever, are not that important. This will allow you to simplify your analysis as well, so you don't have to be doing all these decision trees just to gain a tiny bit more information, and also allows you to understand what's going on, what is really happening in the problem. So they have a very good characteristics. So at some point, I think in the first lecture, I was telling you about explainable AI, right? So here the decision trees come in because when you do deep neural networks, when you do CNNs, you are going to get a result, and then digging out what was the let's say, what was the thinking, quote unquote, of the machine when getting a particular result is quite hard, because if you remember yesterday, we were saying that you start with an input, then you go through this deep network, which makes all these highly nonlinear transformations on the inputs to end up with the output. It's nothing like this very, let's say, intuitive tree of decisions that we are talking about, with thresholds that we can understand as humans. So although decision trees are not that powerful, they are still used when you want to go back and you want to do a post-mortem of your result and trying to understand why it happened. So you will run the same data set with a random forest or XGBoost or whatever, XGBoost, sorry, with the idea that with the deep neural networks you are going to get the best result, but when you run it with a decision tree algorithm, you are going to get some understanding of why this result was obtained. The decision trees won't give you the same level of performance, but at least they will give you some understanding. And why this comes to the issue of ethical AI is because imagine in this problem, that we had added characteristics that are, let's say, socioeconomic. For example, we already discussed the level of studies of the parents of the student. We added the hobbies, the environment of study, and so on. Those are characteristics that are probably influenced by the socioeconomic environment of the student. And it could be that when you try to predict the scores of students, well, it could be going to be the case, that you see that there is a high importance or some level of importance of these socioeconomic factors. So you may want to then think on, for example, how to control over those parameters or those features that are that contain an ethical component. Let me clarify a bit more. For example, in England or in the US as well, the students go along the high school, and at some point, before doing the equivalent of our selectividad, somebody or some board of studies will decide for them what kind of degree or what kind of exams they might be able to get. Okay? So these decisions will be based on previous scores and performance, previous performance. And there is a strong correlation between the socioeconomic level of the student and whether they will take higher studies and what kind of subjects they will take. So, for example, the exam board might take, sorry, I'm going to switch on this because it's bothering me. The Board of Studies may take decisions without taking into account that there is already a bias related to the student's background. Okay, so if we, instead of a Board of Studies, we now let a machine take these decisions, decide that this student is not expected to do very well on a particular subject or is below threshold for a particular subject, then we need to also introduce some level of control over whether these decisions are taken in a biased way. Okay, this is just one example, but in general, is when people are now doing machine learning and the learning and so on, often I'm saying often, this is not that common because in general explainable AI is just starting, it's an incipient kind of level or area of study. But you might want to go back, redo your analysis in a decision tree kind of setup, and then try to understand what's going on. And if there are some of these characteristics that are influencing a lot the result, for example, imagine that this level of studies of the parents was quite important, and this wasn't that important, this other one, then you might want to remove this from your features just to remove some of the biases that you are introducing. Okay, so again, I'm not going to talk for a long time. Yesterday I already talked for too long in this lecture of almost 2 hours. So today, most of you, I would expect, will go over the CNN, DNN minced example. If you have any questions, or go over Slack. I can see that you guys are helping each other. That's great. We will reconvene at 12:30 anyway to hear any kind of questions or experiences with this notebook. But for those of you who finish early or want to explore something else, I recommend you to do this. Let me just give you a quick explanation of what is in this kind of notebook. So these notebooks where we are going to look for signal, which is new physics, and is looking for a particular model for new physics called supersymmetry. versus a background, which in our case is the standard model processes. We would like to find new physics, let's say in the Large Hadron Collider, in the collisions that are happening there. And for that, we need to be able to identify signal events very well with respect to background events. Okay? For those of you who don't know supersymmetry, or SUSY, the idea of supersymmetry is to take and extend, just in a nutshell, the symmetries of space-time, we extend them to more symmetries in the internal space. Let's say, for example, you remember spin, right? It's part of the internal space of our quantum mechanics, and that allows you to define a new type of symmetry, which is called supersymmetry, that is able to change or to transform particles that have a spin integer bosons into fermions, particles of spin 1/2, and vice versa. In the standard model, so what we know is true for the moment, bosons are forces and the Higgs, whereas fermions is what we call matter, so electrons, protons, and so on. So what supersymmetry allows us to do, if it exists, is the ability to connect two different worlds, the world of forces and the world of matter. And in particular, if supersymmetry is correct, we should expect that for a kind of mirror image of the standard model, if the standard model has matter like, for example, electrons, muons, quarks, and also have forces, the electroweak forces, and also the electromagnetic force with the photon, the gluons, and here the Higgs. What supersymmetry will, or a manifestation of that nature, supersymmetric, will be the existence of a kind of parallel set of particles that connect to the standard model particles. But for each boson, for example, for each W boson, you will have an equivalent fermion that is called from the W a Wino, from the Z a Zino, and so on. And for each fermion, like the electron, you will have an equivalent boson, which in this case is called the selectron, the muon, the quark, and so on. The Higgs will be the Higgsino. So it's simply mirroring the standard model particles, changing the spin from boson to fermion, from fermion to boson. Okay, we have not seen this mirror set of particles, but we are looking for them. In particular, in supersymmetry, what you expect is that some of these particles are going to constitute dark matter. So in supersymmetry, you expect dark matter to be some of these partners, if you want, of our usual forces. In particular, you think that dark matter will be some kind of neutral, unstable particle that is often denoted by chi, with a tilde or without, with a zero because it's neutral. And this particle is going to be electrically neutral and also going to be stable. So if among all these supersymmetric particles there is one that is stable and is neutral, what is going to happen is that all SUSY particles, they are going to go or decay into another SUSY particle and a standard model particle, and whatever long it takes, all these other supersymmetric particles, the decay chains will always end up in the lightest and stable particle, which is dark matter. So the prediction, one of the generic predictions of supersymmetry is that when you produce it at colliders, when you, for example, collide protons, those might produce, let's say, a couple of supersymmetric particles, which at some point, and no matter how long the decay chain will be, will end up in dark matter and some standard model particles. Okay? So what you expect from supersymmetry is that well, first of all, what you are going to see is this final state of standard model particles and dark matter. And these dark matter particles that are produced in colliders, if SUSY is correct, these dark matter being neutral and being stable, is not going to interact with any part of your detector. So it's going to leave the detector without decaying, obviously, because it's stable. So it just flies away. And because it doesn't interact, in that sense, it is a particle that is invisible. It doesn't leave a trace. The only trace it leaves is because when we collide the protons, we know that at least in the plane that is transverse to their collision, there must be some level of conservation of energy. And when we see the final state, so when we see a standard model, and we look at the momenta and their energy, we realize that there is some missing energy. The energy that has been carried away by the dark matter particles we have not seen because they are invisible. So a typical feature of supersymmetry is to look for final states where there is a lot of missing energy, which often is denoted by MET or ET with a slash or something like this, where T means transverse, meaning in this plane over here. Okay? So typical features or final states where you will look for supersymmetry is missing energy plus something visible, meaning these standard model particles. Now, from all the possible visible particles you could look at in detectors, the ones that are cleanest and easiest to look for are leptons. At detectors, colliders, leptons mean electrons or positons and muons. The reason is that there are parts in the detector that are specialized to find electrons, and there is also a part in the detector that is specialized in looking for muons. So if in your final state at colliders you have leptons, this is going to be relatively easy to see. And if these two leptons or these leptons come in an event when there is some imbalance of energy, there is some missing energy, this is a possible event where supersymmetry can manifest this. Okay? So what these notebooks that, if you go over them, will do is they have simulated the loss of events with their characteristics of this type. So you produce dark matter, and you also produce standard model particles, and the standard model particles is simply a lepton plus and a lepton minus. So electron positive, muon, positive, negative muons, and so on. Okay, so they are trying to distinguish between, for example, producing at colliders through some kind of interaction. Let's do this. Quarks in the proton can produce a Z boson, so a force mediator of the electroweak interaction, and this guy can then produce a supersymmetric particle that is called a Churchino. This Churchino will decay into dark matter and a lepton plus, and this one will decay as well into dark matter and a lepton minus. So this is what they are simulating. They are simulating these kind of events where you end up with two dark matter particles and two leptons. This is the signal that they are going to simulate. And then the type of background, the type of standard model processes that can lead to the same final state are stuff like, for example, you could have quarks from the proton as well. The proton emits some quarks, and this could produce W's, W plus, W minus, which then produce lepton neutrino and lepton neutrino. This final state also contains two leptons, and contains neutrinos, which are particles that will also cross the detector, leaving no trace. So those neutrinos will also produce signatures with missing energy plus 2 leptons. And this is the background. So the idea is that the people, in a paper, by the way, that they published in Nature, what they did is to show how using deep neural networks, you could improve a lot the performance of your searches for supersymmetry. They simulated, and also for Higgs searches, but they simulated events with supersymmetry leading to a final state of 2 leptons plus missing energy. They simulated events of standard model leading to the same final state, and then they use different techniques, logistic regression, decision trees, and finally deep neural networks to become better at distinguishing signal and background. If you have time, I think it will be great if you go over this kind of analysis, especially if you work in particle physics, because at the end, you see the use of these curves that we were talking about yesterday. Yesterday, we were talking about this, what I call a rock curve. I was telling you about true positives and false positives, false negatives. I don't remember when the equivalent, right? And we were talking about how learning and how well the algorithm is learning depends on how curved and separated from the chance line it is. So we were saying the more it goes over here, the more the algorithm is learning. And I also told you that this was as well something that you would like to look at when you do particle physics. Why? Because let's say that you run your deep neural network and you get this kind of curve. Let's say this one. And you say, well, this tells me how much of the signal I accept, how much of the signal I'm actually identifying. And this, with it tells me how much of the background I'm rejecting, or I'm able to reject. And you will say, okay, so I'm going to work in an operating point where I get the best of both worlds. For example, here at the tip or here at the tip. That means that I accept as much signal as I can, rejecting, sorry, that will be background acceptance, not rejection, it's the opposite. As well as rejecting as much background as I can. Right? I want to be as high here and as low here as possible. As high here and as low here as possible. So this is fine if you had a sample where you had the same amount of signal events as background events. This is what you would like to do. You would like to accept as much signal as you can and reject as much background as you can. But in reality, when we look for new physics, there's always an imbalance. There is a lot more background than signal, and we want to be tighter at rejecting than actually at accepting. We have to live with throwing out a lot of supersymmetric events to the extent that we really need to get rid of a lot of this background. So that means that you have to place yourself maybe in places over here that are not so efficient at the level of accepting signal, but are a bit better at the level of rejecting. So all this is spelled out in the final notebook of these guys when they look at supersymmetry. So again, if you work in particle physics and you do this kind of analysis, you might want to do this notebook. All right, and this is really a lot of talking, so I will leave you to work on the notebooks, either the one of yesterday. And again, don't rush with this. Try to understand the things that are in this notebook, reading up on the different syntax and so on. or moving into this other task, which is just, a task you don't need to complete. Okay. Yeah, Leonardo? Any questions? If not, let's reconvene in 2 hours.
Can you hear me?
Yeah, I hear you. Yeah.
Oh, yeah. Going back to the curve you were showing before, how can we make sure that we are moving to another curve and not along the curve? I mean, what you're thinking about when you are changing inside the model, I guess.
So let me, I draw too many curves. I'm not really good at handwriting, but let me just say, sometimes what we show is an equivalent curve, but let's do the same curve. This curve where we say, this means if you were along this line, you are not learning because you are essentially a 50% chance. Yeah. This means you are learning. And if you get something more curve, you are learning even more. No? This is clear. So this represents the performance of one algorithm, and this represents the performance of another algorithm. Okay, so the idea is that if you get something along this curve, sorry, let me start over. If you have to choose, you will go for the one that is learning more because this one has better performance. Okay. Now, and I think that's the confusion. What I was saying is that let's say that you do your best, you do your analysis, and this is the curve you get, your ROC curve. And you say, okay, well, that indicates a level of signal acceptance, and this is background rejection, or the inverse of that, if you want. How much background I'm letting in. And you will say, well, the best point, where I want to be, is to set the threshold in my algorithm, so I'll be here, in the TPT, right? Where I'm accepting most of the signal, and I'm rejecting, or I'm not letting in too much background, right?
Yeah.
But this is clear. But now imagine that, and it is not always the case, because sometimes you cannot be living here. You cannot be operating at this point, because if you accept all the signal and only reject that amount, you are still getting a signal over background ratio that is too small, just because the background itself is so large. This ROC curve indicates probabilities. Given an event, and my probability of accepting it or rejecting it or identifying it. But it doesn't tell you overall what you need to do, because you might be in a situation where your background is so overwhelming that you have to give up most of your signal to make sure that no background gets in, or not that you reject enough background. So if you have a situation where the background is much bigger than the signal, you might want to operate actually somewhere over here, where you are cutting a lot of the signal, but you are letting very little background to come in. And that choice, where you move along this curve and what point you are going to be operating, depends precisely on this criteria: the significance of your analysis and what kind of background and signal you expect. Is this a bit more clear?
But
yeah.
one question.
Yeah.
How do you move along the curve?
Yeah.
What do you modify?
Yeah, when you... Guys, thank you. So when you run your algorithm, you get as predictions. But let me start over again. Remember yesterday how we were talking about binary classification, and we were saying, okay, so I'm going to use a function that is 0 when it's background and gives me 1 when it's signal. And we were also, that will be a perception. And we also said, oh, but in reality, we are talking about probabilities. So we would like to have something that is smoother. right? That somewhere in between is neither 0 nor 1. It doesn't jump like that. And we want to interpret this as a probability. So given an event, where is the probability that is signal or the probability that is background? And when you declare an event to be signal or background, you will say, well, if my probability of being signal is above 0.5 and the background then is below 0.5, then I say this is supersymmetry, right? But it could be that you want to actually make super sure that you don't let in any background. So you decide that your new threshold to assign a signal event is going to be that your probability of signal is above 0.8, and then it has to be below 0.8. Then you declare that supersymmetry. So you see, the output of my binary classification, logistic regression, deep neural networks, whatever you do, is going to be a probability in each of these categories. And you have to then label the event as signal or background with a threshold for your probability. The logical thing to do will be to say, well, so if the probability is about 0.5, then I say this is signal, and if it's below 0.5, then I say it's background. That's a threshold that is just in the middle, right? But if you want to be tighter, if you want to make sure you reject a lot of the background, then you are going to increase the threshold and say, I will only call a signal event, and hence I will take that event as signal if the probability assigned by the algorithm is higher. It's actually 0.8. Or the opposite, it could be that you say, I want to collect as much possibilities for signal as possible, so I'm going to lower the threshold. As soon as the probability for signal is about 0.3, I take it. So you see, this is like a democratic choice to separate the events between signal and background. This is a choice where you want to avoid to the maximum, or to avoid collecting background events that you misidentify. And this is a looser kind of threshold where you try to collect as many as possible. Any event that has some chance above 0.3 of being a signal, I take it. So that's the way you move through this graph.
Okay, so once you have your model and you predict the results of the test data, then from the result is when you draw the curve, right?
Exactly.
So
there is some in the scalar, there is something that is called a ROC curve. This you build by taking your test. Let's say call it X test. You ask your model to predict the labels for this X test, but you also know the true labels, which are the Y test, which you know. And based on this, you build a ROC curve, which is precisely this. And again, when you say you take a new X point and your model predicts a value, what is going to be this prediction is going to be for the two categories of signal and background, is going to give me a number here and a number here, which is going to be a probability. So it is up to you when you get this prediction to say, well, my label is going to be signal if the entry in the signal is above something, and that's your threshold. It could be 0.5, it could be 0.8, it could be 0.3. What the ROC curve does, it does it for you automatically. It actually takes all these things, looks at this criteria, and then builds this ROC curve for you. Right?
okay, thank you.
You're welcome. Any more questions? Yeah.
I have another question regarding to the increase you mentioned before, and I was wondering how does the decision tree knows which variables are the more stable?
In general, what you will do in, let's say, for example, the example yesterday of the MINST data set. You are not deciding what variables are more important. You are inputting an image where, let's say, you have a 7, which essentially is an image with some spatial information, or the coordinate that you want, and the intensity of light inside that coordinate. And it is not, the algorithm is doing it by itself. It's deciding which parts of this information are more important. This is what it's doing through this convolution and so on. Going through the layers is precisely dropping parts of the image that are not important. It's going to probably drop these parts of the image, and it's going to focus on the ones that have higher intensity or lower intensity, depending on the contrast.
You're explaining neural network, but I was asking about the decision trees.
Yes, very good. Okay, so in the neural networks, in principle, you have no way of knowing which features were more important, and that's why we do decision trees, because there, in decision trees, let's say that we take this supersymmetry example, right? There will be a set of kinematic features, and it will be trying different topologies for all these trees. For example, it could decide that a certain feature, like the momentum of one of the leptons bigger than some number, is a good branching, and then adds another thing, like some angular property of the leptons, the amount of missing energy, and starts building on all kinds of possible trees, explores over topologies of these trees, different thresholds, different entries, and so on. And from all these ones, decides which one is leaving the first prediction. So given the input, goes to this tree, it gets an output, a predicted output, and the decision tree, essentially the whole procedure, is to precisely find which topology for your tree is going to be best. So how do we, afterwards, once we've done the analysis, understand which features are more important? There will be a combination of which features appear first or higher in the tree, and also which features, for example, appear more often. And based on this criteria is how then in decision trees you are able to do what is called, for example, a principal component analysis, or feature importance, and so on. It's not like a simple, straightforward criteria for deciding which features are more important, but the intuitive criteria is that features, when they are important, they will appear often, and they will appear higher. Okay? But again, it's, yeah, go ahead.
So the way the tree decides that a feature should appear higher was by doing a lot of random trees and comparing them. Is that what you said?
What I say is that when you do a decision tree analysis, you don't do just one tree that you decide and you set up yourself, that you say, like in the case of the students, I'm going to start with their previous score. No, you don't do this. You let different trees to be built with different thresholds, and that exploration of all these possibilities tells you which one is a best predictor. And that's the output of your analysis. It's going to be a tree, which is the best predictor, which already has some features and some thresholds already assigned to them. But it's not like you as a human say, I'm going to start with this particular feature because I think it's important. No, that's precisely why there is machine learning in it. It's going to find from all the different possibilities you could write here, with all the different thresholds and characteristics, which ones perform best. And once this is done, afterwards, you can say then that as a, let's say, a byproduct of my analysis, I can identify which features were more important, because they appear higher, they were more important at the beginning, and they also appear often as secondary decisions as well.
Okay, thank you.
You're welcome. Okay, cool. Any more questions? If not, let's reconvene at 12:30. And keep sending questions via Slack. If you haven't signed up, please do, because I can see that people are engaged and they are sending lots of additional material and answering questions. This is really great. Thank you very much, because you are making this a much better course by, participating. So let me stop.